the master from the State University in Ilha Solteira in 2011, and since 2011 he's a PhD student by the University of Campinas. He works in the real-time simulation areas, protection for power systems and electromagnetic transients. Currently he's working with long-distance energy transmission. Thank you, Professor. Good morning to everyone. As Professor mentioned, I'm a PhD student under Professor Cristina's orientation. I'm not a professor, as Camilo has said yesterday. Camilo is a good friend of mine, and he helped me a lot with the project. I thank him for promoting me to professor. And I also would like to thank everyone from the laboratory who works with me daily, especially to Fabián, who collaborates a lot with his knowledge about the relay, because he has worked a lot in this field. More specifically, I'm going to talk about the protection study for energization study of the AC link test. We have been talking about this for the past 2 days, and I'm going to cover 3-phase faults. In the previous talk, single-phase faults were discussed. Now I'm going to talk specifically about 3-phase faults. So it was also said that the lab has acquired a relay similar to the one located in the substation of Serra da Mesa. And with it, we have assessed, or tried to assess, its performance on the energization study. For that, we also use the RTDS we have available in the lab. So the main goal for this work is to study the protection system for 3-phase faults on the energization study. For this, it is necessary. First, it is necessary to analyze the current protection system in the substation of Serra da Mesa. Check if it would be enough to protect the AC test link, because it was designed to protect the segment, only a segment of the line, and not the half-wave length line. So we need to analyze if its adjustments are enough, if the hardware available is enough. And after that, we need to study some special adjustments, change the conventional philosophy we have, which is the protection to long distance, so we can have a better performance in the protection system for the energization study when we have 3-phase faults. So the proposed circuit is also well known. We have to use the 3 trunks of the Brazilian electrical system. The sending terminal is the substation of Serra da Mesa 1, and the receiving terminal is the substation of Bom Jesus da Lapa, whose circuit breaker is always open because we have a non-load energization test. For maneuvers, we can only use the circuit breaker in Serra da Mesa 1. We call it Serra da Mesa 1 here. And it is connected with the 0321 relay that we have in the laboratory. So all the other circuit breakers are always closed. We have in this line of 2,600 kilometers, the power relation is 4,500 to 1, and the current rate is 3,000 to 1. The system was modeled in RTDS. This part of the work was conducted by ELSO. This is a very complex system. So here we have the current signals, current transformers here, and power transformers here. And we work from here is where we get the signals that are sent to the relay. In addition, we implemented a component in our TDS which allows for the calculation of the apparent impedances for a previous analysis to the relay test. So it was implemented by using the C language, and we use sampling, calculation of the factors, retentions and currents, and also the impedances. So analyzing the conventional protection system, we have that the protection system in the substation of Serra da Mesa 1 was designed to protect the segment of line between Serra da Mesa and Gurupi with a primary protection system. And it should also supply protection, backward protection for this segment between Gurupi and Miracema. And perhaps it also has a third area to protect, which is this other segment after the third substation. We have put here 20 ohms of fault. That's why it's not at the origin of fault impedance. For faults, and this impedance seen in Serra da Mesa 1 for faults happening in this segment. So here we have a conventional behavior that is expected by everyone using line protection. We almost have a line here, so we can use the distance protection, for example, for protecting the corresponding segments of the line. But here, in a half wavelength line on the AC link test, we are looking this more from a distance because the impedances would be like this with the whole line. So this would not be so expected. Perhaps it would be expected for it to go up a little bit more, but it will be a curve. And it can go around. Up until this point, when it crosses the real axis, the half wavelength is exactly what is left until Bom Jesus da Lapa, and what's remaining is a little bit more than half a wavelength that was mentioned before. Half wavelength, we have one cycle, a complete cycle. Here it's possible to see that the distance, conventional distance protection would not be able to protect the whole line. The relay that is found on the substation, it has a maximum reach of 320 secondary ohms. So we would be talking about protecting only this segment that I'm showing you here now. And what would happen to the rest of the line? So here we have that the impedance without fault is here on this little square. We know that between Serra da Mesa 1 and Gurupi 1 there is a distance, there is a physical distance of 250 kilometers. Between Imperatriz and Colinas 2, 330 kilometers. But between Serra da Mesa 1 and Gurupi 1, 250 kilometers, and between Imperatriz and Colinas 2, 330 kilometers. They are almost identical. There's 80 kilometers of difference. However, the impedance between Imperatriz and Colinas 2 changes a lot more. Another special characteristic for half wavelength line that we are able to see when you have three-phase fault is that when three-phase faults happen, they happen in the segment of the line, because large overvoltages only happen throughout the line. And this happens very fast. For example, here we have the voltage profile for a three-phase fault in Serra da Mesa 2, which is located at 2,000 kilometers of sending station. So it's 3.5 PUs above. To mitigate large voltages happen throughout the line, large currents, including on the maneuver circuit breaker, so it will not be possible to do a safe maneuver. So in order to remove this condition of almost quasi-resonance in the line, it was also mentioned before that we need to use a method of reduced isolation distance that allowed for a discharge to be made in the Imperatriz substation, removing this condition from the system. Here we have the overvoltages for a fault happening in Imperatriz, which is approximately 1,000 kilometers away from the sending station, and we can see that it has never reached 1 per unit, 1 PU. The reduced isolation distance put in Imperatriz changed the impedances we found in Serra da Mesa 1 for faults happening in the end segment of the line. When you have a fault in the end segment of the line, it was possible for the impedances that we found here on this way to skip to this other point more above. So if we try to design a protection system, we need to take into consideration this behavior of these impedances. We need to take the reduced insulation distance into consideration. Besides that, we also analyzed the voltages and currents seen in Serra da Mesa 1 for faults throughout the line. Here we have the voltage seen in Serra da Mesa 1, and then we have the voltage without the reduced insulation distance. And in green you have the voltage using the reduced insulation distance. And in pink we have the voltage in stationary stations without fault, stationary states without fault. And in the beginning of the line we have the expected behavior. We have fault and the voltage goes down a lot. And as the fault becomes more distant from the sending station, voltage increases. This is what would be expected. The voltage continues to rise until reaching a point where we have a fault, and the voltage is the same as the voltage without the fault. And then the voltage found in Serra da Mesa 1 when we have a fault, here after half the line, it's larger than what the tension without fault would be. So in blue it continues to increase until it drops again in the final segment. We saw that the reduced insulation distance held the voltages in this segment for these values you can see in green. So this is a specific behavior for this type of line, looking at the voltages. In the current, this is also what happens. In blue, you have the behavior without the reduced insulation distance, and in green the behavior with the reduced insulation distance, and in pink without fault. So for faults happening in the beginning of the line, the current rises a lot in comparison with the current without fault. As we move away from the sending substation, current drops. But it continues to drop until it becomes smaller than the current without fault. So here, when a fault happens, and the current found in Serra da Mesa 1 is smaller than the current without fault. So this is a specific characteristic for this type of line. After that, it begins to rise again, and after the final segment for larger currents until faults that happen in the substation of Serra da Mesa 1. In green, you can see that the reduced insulation distance had held these currents. So with that, we can see that it is possible to use overvoltage devices to cover the beginning and the end of the line. At least in this segment, if we use the reduced insulation distance, we can accomplish something. And for sub-voltages for the beginning of the line and also in the end, and over voltages as well. So in addition to the reduced insulation distance, we can also use this device. But why do faults in the middle of the line, why are they complicated? To show this, we have all the voltages and the currents for faults happening in Colinas 2, 1,300 kilometers from the sending substation, exactly in the middle of the line. So here we have that a fault happening in Colinas 2. The voltages in the Serra da Mesa 1 substation, Gurupi 1, Miracema 1, Colinas 2 until Imperatriz, they basically do not change. They were not, no disturbances happened. Only the voltages in Colinas 2 and the substations forward was in a sub-voltage state. Here we also have the currents. The same thing happens. There are basically no changes in the currents, not even in the Colinas 2 substation where the fault happened. Current is basically the same. Only in the substations ahead, the currents decreased. So it's possible to see that identifying the three-phase fault in the middle of the line is very complicated, just using measurements in substations, in the substation of Serra da Mesa 1. So we have here the adjustments we could make for the relay 0321. We used one to cover this beginning of the line, zone 2 with maximum reach of relay being 321 to cover this region. And we also used here something that would not be used, using the reverse zones 3 and 4 to protect the final segment of the line. So here, the zone 1, the relay shows in which zone the fault was found according to the adjustments that we set up. So if it shows zone 1, we also have information that it happened on this area of the line. If it shows it in zone 2, we have the information that the fault had happened in this area, in this segment of the line. And with areas 3 and 4, that's why we used 4 zones, because we could have used only 2, one ahead and one reverse, and one behind. We also used the concept of under voltage or sub-voltage of 0.84 pu, over voltages devices of 1.2 pu, and the over voltage relay with these adjustments. A large amount of tests were conducted on the relay we are using RTDS for this. So as I mentioned before, we used 21 of fault impedance. And here, this is what we have. This is the line. And on the first line, we have, this is in English because this is a graph we presented in a congress in Canada. So here you have RID would be the reduced insulated distance. The RID always works for faults happening in the end segment of the line. And then we have the individual performance of the RID for voltage, current, sub and over voltage, under over voltage. And on this line, the distance device is working without RID, and it starts working in the beginning of the line, as we said, zones 1 and 2, and then again after half the line, and also in the final segment of the line. When we include RID, the performance in the beginning of the line does not change, but in this segment, because RID is working, it removes impedances from the protection zones, and we do not have the distance device working anymore, except in the final points, which is a little bit more than half a wavelength. Here we also have the performance of the under voltages without RID. It didn't change when we actually used RID. The under voltage device without RID, a little bit after the beginning of the line and also in the end of the line, over voltage, and it also work in complement to the sub under tension, under voltage device, but not except in the middle of the line, because we created a gap between 0.8 pu and 1.2 pu. And then we have the device, under voltage device with RID, and it does not work in the final segment of the line. It blocks the under voltages, and the same thing happens with over voltages. Finally, we conducted tests using all the devices with the trip logic, and what we have here is a logic behind everything that was expected. So the 480 kilometers in the middle is left unprotected, and this performance did not change when we used RID. When we added, the result was the same. So as we have shown, the substations, when we have a fault in the middle of the line, the forward substations after Colina 2, they are on an under voltage state. And since the substation of Serra da Mesa 2 is physically close to the substation of Serra da Mesa 1, we saw the possibility of analyzing the behavior of an under voltage relay located on the substation of Serra da Mesa 2. So here we included an under voltage relay on the substation of Serra da Mesa 2, because we could have a possible communication with the substation of Serra da Mesa 1, because they are physically close to each other, so it could protect the central segment of the line. We can see that altogether, if you have a relay located in a substation of Serra da Mesa 1, and together with it we use an under voltage relay on the substation of Serra da Mesa 2, we would be able to protect the whole AC link completely in the energization study with non-load. In addition, we conducted tests changing the transformer relations in the current transformers, because if we drop the rate the impedances in the secondary will also be smaller. So we have a higher reach, considering that the maximum reach for the circuit breaker relay is 320 secondary. So this study is very similar to the previous one, but what is important here is to highlight that we have a segment of 380 kilometers in the middle of the line without protection. So we could not protect the whole line anyhow. And we had an improvement here of 100 kilometers. Finally, we have our conclusions. It's important to highlight that the conventional protection philosophy for transmission lines for long distance as is not enough to protect the AC link during energization tests. The relay located in Serra da Mesa 1 protects the line, except a central region of 480 kilometers. When we change the ratio to 750 to 1, we have had an improvement of 100 kilometers. Using the relay in Serra da Mesa 2, the whole line was protected for the energization test without load or non-load. And finally, we could see that faults happening in the middle of the line are difficult to be identified, but they are not severe. They're not critical to the electrical system. They behave as faults with a high impedance, with very low currents. Voltages do not change as well throughout the line. Thank you very much.
O microfone não está funcionando. No. Yeah. Em outras palavras, the philosophy would be the same. We have a system that simulated basically the situation of maximum load, and then we have a line model that is valid for conventional and long lengths.
ты раз, два, три, четыре, пять. Сколько ты уже принимала? Сегодня ты приняла 2 передо мной. 2. Здесь 1, другой там. А сейчас? Сколько их можно?
The simulation parameters were the same. We did the same simulation with the 50 microseconds, which is the minimum allowed by GTS, and we also used the Berger line model, which is the distributed parameters model, which was the same. This simulation of the electric system did not have any special consideration because of being half wavelength line. The idea to open the middle of the line would be to use telecommunications up to Serra da Mesa 1, or would there be circuit breakers, local circuit breakers closer to the middle of the line to do this opening? Understood. Here we analyzed a possible communication. How that would be made is not part of this work, but since it's physically close, it was an substation, Mesa 2 substation, yet, because that would require 1,000 kilometers of telecommunication. Now, physically, electrically, they are 2,000 kilometers. Physically, they are the same substation. They are 2 parallel lines. Yeah, I know. Physically, not that. I say. Because in this case, the implementation of the line went and came back. But in practice, the half-wave length line will have 2,600 kilometers point to point. So my question is this: if to implement in the real case, your idea would be to have a relay with communication with the sending substation, or would you see circuit breakers closer to the middle line to do this opening? The case of the work and the project is based on energization test. Here you can see there are a lot of more problems than that here. We have no load. That's a constant. The real system, we would have load variation and would have to develop specific protection, and there are a lot more considerations than what is shown here. So it was shown that there is difficulty to identify faults in this is the protection of the line and its operation. So actually you cannot close the middle of the line without having communication between the substations. So you have to have information. Since you're gonna have relays at both ends, the second relay will see sub voltage. The no load line, for instance, the Bom Jesus relay would see, and you would have to include the time for this signal to get to the sending terminal. So we're still developing that. Renzo is getting results. We have many interesting results, for instance, for it to identify the fault phase. So there are many things which are specific of the, but certainly you'll need a transfer trip. In our case, are we going to work with the Serra da Mesa? Can we work with the Serra da Mesa too? Since it is physically close, it's possible to simply pass to install a cable to have the whole control from Serra Mesa 1. So should there be any defects, or could it be a consideration of the test not to protect the line for the three-phase fault, hoping that Vanderlei's plane never falls there? Last one. Can I just say one thing? I think that he also asked about the circuit breaker in the middle. There is no middle circuit breaker. Just a sec. Because a possible extension would be, after a while, the half wavelength can be interconnected and become stretches of conventional lines, so the cost of the circuit breaker in the future could be compensated. But Sergio, we cannot have an opening in the middle of the line. So you wanted just a protection, not the circuit breaker. Yeah, because that we would need a reactor. You wanted just a protection. You would like to have some measurement in the middle of the line. Was that it? A sensor in the middle of the line. Because not a circuit breaker. The idea is that when we had a fault in the middle of the line, the circuit breaker would operate, but the circuit breaker cannot operate the line in the middle. Yeah, because there will be an additional overvoltage. So you would really need to have, necessarily, I need to have telecommunications to those who can open the line are the terminals at the ends, like a link. Have a question or gave up? One minute. So I'll talk just 2 minutes to shorten my time, and then now to have any questions. Cristina, the thing is, since yesterday I have a question I didn't want to take home today. And now, with this thing of the difficulty of sensing failures at the central part of the line, trying to use the relays, the existing relays, so on and so forth, I think there comes to make me more anxious. I do not know if it's up to him, up to everybody. I know that on one side you have either I do it with the existing surge arresters, or I can't do the energization test. This is a question that is still here bothering me since yesterday. And then all studies are being performed, taking into account that energization will have to be done in this part here, and only then with the compensation turned off shunts, but the surge arresters will have to be present. And then we saw yesterday and today in the morning a little bit more certain cases of the actuation of the surge arresters. That was one thing. And then I am here. That is something rather of faith. But as I am a man of little faith, and just like me there can be many others, that's the thing. If this person of little faith will come to you and say, yeah, you could successfully energize only thanks to the surge arrestor, which is not present in a real case, so you did no test at all. Just one thing before. That would be the voltages and currents when there is a fault in the middle, and it does not put the system in a severe condition. Just to close this, the thing is, if you can do this test, because to lose more than what we are in terms of credibility, we can't, but we can worsen it. Imagine in the case of energization, there is some protection actuation, and if there isn't, there is thing. Have you really tested a real line? Because in a half wavelength line, in real application, those surge arresters will not, that consumed energy will not exist. Well, Mauricio, the surge arrestor can only consume energy if there is a fault. Otherwise, it won't actuate. That was my first presentation where I show the tension curve with and without surge arresters. So terminal voltages don't change, the profile doesn't change, the energy along the link in the no fault energization maneuver, the voltage is very low. With the fault, then since there are surge arresters for some people, for some cases we'll have the actuation of the surge arrestor. You see that in the case of single phase faults, in the critical area, the surge arrestor that suffers is the one in the line. So if we didn't have the surge arresters, all of them, or the others, they would have to dissipate all that in that. But then you would have bigger voltages, but they wouldn't cause disruption because the voltages are high. So you have the curves with and without surge arresters. So those voltages are not high. They actuate, but wouldn't have to break, wouldn't get to break arcs. You would have the surge arresters at the ends being more demanded, specifically the Bom Jesus one. As Weissman asked, have you considered the type of actuation of the circuit vector? We did fast actuation. We can have 50 milliseconds. We could have 3-4 cycles to for the actuation of the circuit breaker. The energy at the surge arrestor is going to be bigger, but it won't blow as surge arrestor there is today. For three-phase we need to reduce distance of isolation in imperatives, which is a procedure that is used at the entrance of substations today. The substation doesn't have anything. It's not something that's special. We don't use that in the middle of the line. There are no lines that long. With that fragilization of the chain, you don't have severe disturbance, even in case of three-phase faults. All works, all papers, all references, three-fault phase was always considered with great care. When Renzo showed here 3 pu, 4 pu, we have papers showing those values, but those values aren't real ones. They never really happen because the isolation coordination of the lines, what would happen when you got to 2.5 pu? You would break the arc. If you didn't have a surge arrestor absorbing the energy, there would be the rupture of the arc with 2.5 pu. So you don't get to that voltage. What we are doing when we fragilize the isolation chain in Imperatriz, we are forcing this arc in a place that we know is proper. I'm not going to let the arc break anywhere. Because 4 pu, if you get an article saying the voltage will get to 4 pu, the person was lost in simulation. Simulation says 4 pu, but actually it doesn't get to that because it's going to break the arc before that. Where it breaks the arc, automatically removes it from the quasi-resonance situation. I don't like to use the name resonance here. Because of the half-wavelength, we're going to have very low impedances in the area of the half-wavelength. The positive sequence, because then the conditions of quasi-resonance, and then this condition, the higher over voltage is going to happen in a fourth. It's always the game between 1/4 of length and half wavelength. 1/4 of.
И тогда идет оно
at my substation, so the voltages they go down. Serra Mesa wouldn't break arc. The surge arrestor will have to withstand the energy, but Imperatriz, since it will start raising, and it never does because its voltage is low in this energization level. When it gets to 1.6, I know that I am in a condition that is extreme. So I fragilize it, I hold this resonance. Something similar to this has to be thought for the power transfer operation, but not. I do not agree with what you say that the surge arresters are hindering, that are absorbing. This is not true. What we can monitor during the test, the energy in the surge arrestor, what actuated, what didn't, and then we do the math backwards. Sorry, Cristina, I think I didn't express myself properly. It is this: I am not against, but those against, will they give credibility? Will this test serve only for no load energization, and if it is performed, and unfortunately any discharge in the surge arrestor happens, aren't you risking to lose more than what you're going to get? No, if a defect happens and there is actuation of the surge arrestor, you know it did. We have all simulations to confront with the case that may happen. So we know the energy that is passing by. We'll see the operation. The circuit breaker will open at the right moment. So what I believe is not ever to be done is a strong study like that done. That's never going to happen in Brazil. A study that was done in Russia, where they had load applied, they applied the defect. Our proposal is a no load energization. Quite safely we could put some load at the end of the line, because the load would be a small one. Our line has 1,000 megawatts, the characteristic power of 1,000 megawatts, so some load in Bom Jesus wouldn't be that difficult to have. But you'd need some more negotiation. The no load test is already enough for us. Can I consider that can we move on to the next lecture because of time? Thank you.